Привет! Thank you. It is so easy presenting at a foreign language conference. It is so easy to please you. So I appreciate that. Thank you for bearing with me. All right, today my presentation will be on threads and about them not being evil. So I'd like to start off by saying threads are not evil. Thank you very much. Does anybody have any questions? Okay, so just kidding. I do have some actual content. The year is 2008. Ruby 1.8.7 has what's known as green threads. These are threads that are scheduled by the Ruby interpreter instead of by the native operating system, leading people to say, Ruby doesn't have threads. This is a huge limitation, leading people to not use threads in Ruby. In 2011, Ruby 1.9.3 introduced native thread support. Yet there are still lots of limitations. Ruby has what's known as the GIL, or Global Interpreter Lock, which prevents multiple threads of Ruby code from running at the same time, which leads people to say things like, Ruby cannot use threads. And now it is called the GVL, and I will talk about this more later. The GVL ensures that the internals of Ruby are thread safe, but it doesn't necessarily help the programmer. Rails adds a feature called rack lock. Rack lock actually prevents your application from using multiple threads at the same time, leading people to say Rails cannot use threads. In 2012, this configuration option was added to Rails to allow you to actually use threads with Rails. But when people did that, they found that their application code is not thread safe, leading them to say, my Rails and Ruby cannot use threads. What do you hear? I hear doesn't, incapable, not able, will not. In 2012, Sidekick is released, a backend queuing library that uses threads. In 2013, Heroku, which I work for, introduces Puma as our new default for all of our documentation, which comes with a hybrid mode that includes processes and threads. Still, we hold on to these words, doesn't, incapable, not able, will not. If you tried writing threaded code, you know that it is actually incredibly difficult and is not easy at all. So instead, it's easier to tell ourselves comfortable lies. Doesn't, incapable, not able, will not. Before we talk about threads, I want to talk about sailing in 1490. So please come with me, if you will. The decade is 1490. Leonardo da Vinci is alive and well. Russia just built the Ivangorod fortress. I don't know if you get that reference. I just looked up 1490 and searched for Russia. Some guy named Christopher Columbus discovered a new world. And this is 1490. This is where we are right now. And if you travel back in time to 1490, you will discover that the greatest, most powerful invention of the time was the sailing ship. And these powerful items were the object of everyone's desire. Built of oak by hand, they were marvels of modern engineering. You might recognize sailing ships from the majestic statue of Peter the Great that everyone loves in Moscow. Yes, yes, I'm told it's quite the envy. I was told you all would get that joke. Okay, so these ships cost huge sums of money and could only be afforded by extremely wealthy companies and countries. Of course, not just for a status symbol, for hundreds of years, they ruled the seas for warfare as well as for global domination in commerce. And building a larger ship meant that you could stay out on the water longer, and that meant a country had an edge. Big ships meant more storage, this meant more supplies, and more supplies meant that you could sail longer and further than your competition. Unfortunately, humans became the weak link. Who here has heard of scurvy? Okay, I Google translated this, so, all right, I'm seeing some heads nod. Good. So scurvy is a very serious disease that you get when you're deprived of vitamin C. With scurvy, you feel tired, you feel weak, your body cannot repair itself. Eventually, you die because of uncontrollable bleeding or infection. One explorer wrote of scurvy that death is a merciful release. So scurvy is a very serious problem for the countries and the companies as well as the sailors. The solution is very simple, vitamin C. Scurvy is the process of not having enough vitamin C in your body, and vitamin C is found in most fresh foods, vegetables all have vitamin C. Unfortunately, sailors back in the day would only eat processed food, so dried, cured meat and hardtack, which have no vitamin C. Sailors found that the disease only happened when they were away from port for an extremely long time. If they stopped and were resupplied, then the disease went away. Unfortunately, you can only keep fresh food with you, so they needed something better, which led them to citrus. So they found out that if they brought lemons with them, lemons are naturally high in vitamin C. Unfortunately, back in the day, they didn't distinguish between lemons and limes and oranges. They just called all of them citrus, and most of them would be picked green, and it would actually be relatively hard to distinguish between the two of them. So they called all citrus limes. And this is actually where the phrase, if you've ever heard of a limey, is a slang for a British sailor because they would drink lime juice and I guess smell of lime, which would be relatively unusual for a commoner. So in 1869 or 1867, bringing citrus juice was actually a legal requirement on all British sailing vessels. So problem solved, right? We know what the problem is. We know what the solution is. Unfortunately, the cure for scurvy would be lost and found again and again and again and again for hundreds of years until the early 1900s. The British Empire actually changed their supply of citrus from Mediterranean lemons to West Indian limes because they thought these two things were the same, and they're not. The common knowledge at the time was that citrus cured scurvy. Strangely, when this change was made, nobody noticed because the feedback cycle was too slow. Steam travel had just been invented, and people were getting places faster, and diets were improving, so they had more vitamin C in their system just naturally. The issue is that while limes also have vitamin C, it quickly deteriorates and degrades, so making lime juice nothing more than flavored water. Well, lemon juice actually has lots of vitamin C when you juice it and keep it. So, which leads me to the question of why am I talking about sailing ships in the 1490s and a technical talk about threads? I'm glad you asked that question. So, when people forgot the lesson that led them to a cure, they forgot the cure. Well, the Ruby language ecosystem continues to be more friendly towards threads. People's fear and misunderstanding of threads leads them to be stuck in the past. So, it is my job to bring you into the future. Costume change. Okay, so by the way, my name is Schneems. You can find me online as @Schneems on Twitter. I have a website, schneems.com, with a mailing list. Please go there and sign up. And I have a website called codetriage.com where you can go sign up if you're interested in getting involved in open source. It's codetriage.com, codetriage.com, codetriage.com. All right, I also work for a small company based out of San Francisco called Heroku. All right, who here knows what a thread is? Okay, who here really knows what a thread is? Okay, you're going to find out. So before we can talk about why threads aren't evil, we need to dig into exactly what a thread is. And before we can talk about that, we need to understand what a process is. So this is a process. A process is basically a giant chunk of memory with a bunch of things in it. For example, it stores code, it stores data such as variables, and it's got a register and a stack. A program is compiled to run on a CPU. For example, here's a short C program, and when we compile it, it turns into instructions that look like this. And this is nothing more than, instructions are basically nothing more than a bunch of memory chunks. And when the program gets run, we actually are going to execute those memory chunks. They're going to be pulled and then run on the CPU. There are two really important parts of the process. There is a program counter, and the program counter we can think of as an arrow that is pointing to where our program is currently executing. As the program runs, this location is kept on the CPU in a register. And whenever the program has to be preempted by another program, it's stored inside of a struct that we can then load back on the CPU so we know where to begin again. There's also something called a stack, and this keeps track of the depth of our program. For example, here we have a call to the increment function. Whenever we call this increment function, it will go up here and call our code, and eventually it needs to return. But when it hits this return code, what actually happens? Well, it looks back on the stack and says, where were we previously? It'll discover that it was right here, so it'll go back to the previous context. So the stack is used to determine the call location of the program and resume execution. So thank you to Julia Evans for posting this C code, and you can get this example with also some more information about the stack on jvns.ca. Okay. At this point, we've roughly got everything we need to stop and start our program, including a program counter and a stack pointer. And this is really, so we need one way to store and load this data whenever we want to transition between programs, and it goes into a structure called a process control block, or a PCB, which includes things like process state, number, program counter, registers, memory limits, and some other things like signal masks, which we do not have time to get into today. So fun fact, whenever you call fork on a program, on a process, basically all you're having to do is copy the PCB from one program and put it into another. So the process control block, essentially, for all intents and purposes, in the operating system, is the process. So back to a process. A process can do pretty much two types of tasks. The first type of task that we would normally think of a program is a very CPU-intensive task. This could be calculating prime numbers. This could be doing some sort of hard calculations. And when you're doing this, the process is using the CPU intensely. It's running and running and running and running. The second type of task a process can do is called I/O, or input-output. So with this type of a task, it could be reading and writing a file. It could be making a call to a database, or making a network call to, say, the Heroku API. As you can guess, with an I/O task, based on my little clip art here, it doesn't do much when the I/O is being performed. The process actually goes to sleep, and it just sits there and waits for data to come back. So when we're doing an I/O task, we're not really using the CPU at all. This matters because we pay for our CPU time. We pay for our processors, and we don't want our program to just be sitting there not doing anything. We want to maximize our CPU utilization. So how can we do that? If we have one CPU-bound task and one processor, then we're set. We're going to use all of our CPU, and it's working all of the time at maximum speed. But whenever we introduce an I/O task to this process, then suddenly we're no longer using our CPU full time. So what can we do? One of the ways is that we can actually add an additional process. So while one process is sleeping, the other process can be working. And so in this way, we're more efficiently using our resources. What are the pros to this? Better utilization of the CPU is definitely the main pro, but it also has some cons. We need a lot of processes in order to do this. And processes also take up memory. We talked about each process has code, each process has data, each process has a register, each process has a stack. And memory is a finite resource. Loading and unloading a PCB is also expensive. And sharing data between processes is hard. Wouldn't it be really cool if there was like some kind of a lightweight process, something that used less memory with a smaller time to context switch? If only there was such a thing. I want to introduce to you threads. Okay, so if this is everything we need to run a program, with a thread, we can share code, so we don't need to duplicate that. We can share data, so we don't need to duplicate that either. Really, all a thread needs, mostly, is a register and a stack. So when you think of a process, you can think of a process with a single thread in it that has an individual register and an individual stack. Whenever we have multiple threads in that process, then each thread has its own register and its own stack. So we are duplicating that, but it's sharing code, and it's sharing our data. What are the pros of this? Well, better CPU utilization. It's the same, which is good. However, we also get to reuse existing process memory. Previously, if we're duplicating our process every single time, that's using more and more and more memory. It also takes less time to context switch in between threads. And unfortunately, there are some cons to threads. So one of the biggest benefits of using a thread is that we have shared data as well as shared code. And that's what buys us a thread. That is basically the definition of a thread. Unfortunately, when people talk about not liking threads and not being comfortable with threads and really hating threads and calling threads evil, this is what they're talking about. Having to program around that shared data and that shared context is pretty painful and pretty difficult if you've not done it. However, the core value add of a thread is having that shared code, but it also adds complexities. And I'm telling you this to try and demystify some things. At the core, threads are relatively simple. It's basically a process minus a couple of things. However, threads are also very difficult, and I'm not gonna try to sell you and tell you a comforting lie and try and convince you that threads are really actually not. And this is true in every language. This isn't just Ruby. This isn't just our language that we're using right now. This is also true in pretty much every language that it's possible to use threads. It is possible to avoid threads. For example, if you're using JavaScript, it is single-threaded. It is evented. This means that we cannot introduce new threads, so we don't have to deal with threading, which is one way to get around the problem. Another way is to make threading easier is to avoid mutating data. So if the problem is that we have shared data between different threads, if we don't ever change any data, then we can't possibly mess up shared data. So certain functional languages get around this by not allowing you, by being very restrictive in what you can do with your programming language. And personally, I feel like while this makes threading easier, it makes all of the rest of coding more difficult at the expense of being easier to use with threads. Right now, I'm taking master's courses at the Georgia Institute of Technology. I have a bachelor's degree in mechanical engineering, and so I wanted to learn what it was like to get a computer science degree. So I've been taking courses here. And one of the courses I took was a operating systems course, which conveniently taught me a lot about the internals of threads and processes that you're hearing now. One of the assignments was in writing multi-threaded programs in C, and I can tell you that it was, having written a bunch of Ruby threaded code, it was so very painful. Much more painful, in fact, than Ruby. And so, well, I won't say that threading sucks in Ruby. I will say that threading sucks less in Ruby. OK. Are threads just for performance? That's all I've really talked about so far. Talked about I/O and getting more throughput. We can actually use threads for a number of other things. Here's an example of some code that I have in one of my gems called Puma Worker Killer. So what does it do? With Puma Worker Killer, you say, every 4 hours, I want you to go kill some Puma workers. It's pretty self-explanatory. And this is the actual code from my gem. We start up a thread, we sleep for a certain amount of time, and then we call reap, which basically just goes through each of the workers and restarts them. Was that scary? Audience participation? Are threads scary? No, it's not that scary. And again, that was the actual code. I didn't simplify that. What about another example? So here is Scout. Scout is a performance monitoring library. I really like Scout. If you're familiar with New Relic, it's kind of a New Relic competitor. And what they use a thread for is they store metrics about your application in the background, and then they kind of bundle it all up, and then they send it to their server whenever they can, just in the background so it doesn't interfere with your program. All right, so those are two examples of things that we can do with threads that we can't really do otherwise. We can't really do things in the background without threads. Previously, I mentioned the GVL. Who here has heard of the GVL, other than the fact that I mentioned it earlier in the presentation? OK, so GVL stands for Global Virtual Machine Lock. And if you hear somebody say GIL or GIL, it's the same thing, just a new name. OK, so here is some example code. We have an array that is being mutated by one thread, and then it's being mutated by another thread. And when we run this program, we get relatively expected behavior. It just outputs hello world about 100 times. OK, there we go. So the GVL puts a lock around every single call. So whenever we call prepend on this string, the GVL is saying no other thread can be running Ruby code right now. So even though we have two separate threads, only one of them can be calling prepend at a time. Likewise, over here, when we are appending the word world to this string, no other thread can be running Ruby code. And the reason for this is the internals of Ruby are not necessarily thread safe. And so to get around that, to allow running your Ruby code in multiple threads without any kind of seg faults or errors, Ruby uses a GVL. And this is not unique to Ruby either. If you're familiar with Python, Python also has a GVL. So the GVL means that we cannot see a speed increase just by introducing threads, which is kind of sad. However, if we remember our previous example, when is it really good to use a thread? Well, it's really good to use a thread whenever we have I/O. OK. Luckily, the GVL is released whenever we do I/O. So that means that using threads inside of Ruby is a great, great candidate to get performance in the #1 case where we want to be using a thread in the first place. So if I change my example, and instead of just running Ruby code, I'm doing something else. So in this case, I'm using net HTTP and making a network request. So while I'm doing that, each thread has to sit there and wait for that request to come back before it can actually before we can continue and process data. So this would actually run both of these in parallel. That does leave me to ask the question of when exactly is the GVL released? OK, there are two main functions inside of the Ruby source that you can use. If you're writing your own C extension, you can use these directly. RB thread call without GVL and without GVL2. If you take a look at the Ruby PG library, you can see that it's using one of these. And you can actually run your Ruby code and with a debugger, if you're using a Mac, I'm sure the debuggers exist for other operating systems as well, and see when the GVL gets released. So in this example, I'm using LLDB, which stands for low-level debugger, and it's on a Mac. You specify the executable you want to run, which is Ruby, and then the program you want to run, which is, in this case, scratch.rb. We tell it to break whenever it hits RB thread call without GVL or without GVL2. We then tell it to run. This will begin the execution of our program. And then whenever it hits one of those functions, it's just going to stop. At that point in time, we want to know where we are, so we can use the backtrace. So Ruby's backtrace function is called RB_backtrace, and we can just go ahead and use that directly in our debugger. OK. If we were to run this program, where do you think the first break would be? Do you think it would be at puts? Or do you think it would be at net HTTP get? Or parsing the URI, creating the string, or requiring net HTTP? OK. What if I told you that it was a trick question, and it's none of the above? If we run this and we use the debugger, it'll pause way before it even gets to our script. Because internally, Ruby has to use require as it's booting up, and this will go out and read files, and whenever it's reading a file, it's doing I/O. And so that's going to release the GVL. So a little bit of a trick question. I mentioned that because it surprised me as well. If we actually get back to our program and we let it continue, these are the two places that it will pause and that it will break. So require net HTTP, whenever we require a file, we have to go out and actually read the file and parse the Ruby code. And the second is the actual net HTTP call. All right. I did tell a small lie. These are not the only two times that we can release the GVL. There's also some macros internal of Ruby, and you can break on them. I don't recommend it. By the way, you don't need to know any of this. This is all entirely kind of just for your own information, really to show that it's not magic and that threads aren't evil. So it's not magic, and threads are not evil. Okay. All right. You're with me. Good. Okay. So how do we start using threads? If you're like, man, this is really interesting. I haven't explored threads. I thought threads were awful in Ruby. Well, I would invite you to make a toy threading library just for fun. Nothing necessarily that you have to introduce and push into production. We can start by making a threaded worker. So first, we have to introduce some sort of a way to pass data to and from our thread. In order to do that, we need a queue. Next, we need a thread, so we call thread.new, and we give it a block, and whatever is in the block, our thread is going to run. We loop forever and ever and ever until the heat death of the universe. And inside of the loop, we call queue.pop. And so this is going to, whatever we put into the queue, we are going to get out. And then we call call on that result. So presumably, we are putting in a lambda or a proc. Now we want to know, how do we use this code? So this pattern is called a boss worker pattern. So that was the worker. Now we need a boss, which is just going to be our main program. So in this case, for 10 times we're looping, and we are creating 10 different proc objects. Again, we could also use a lambda. And then we're just pushing them onto the queue. And when we put it together, it works. We get puts hello about 10 times. However, there's still going to be bugs. We need to ensure that all of our jobs are finished before we shut down. And so we can do that by joining the thread. So here's our entire program all put together. At the very bottom, we call mythread.join, which is basically saying, like, OK, thread, as you know, once you get here, you need to shut down before we can continue. Unfortunately, this causes an infinite loop in this case. If you noticed before, we actually have an infinite loop in our code. And so if we are trying to wait for this thread to shut down, it just won't. So one of the things that we can do is called poisoning a queue. So we introduce an object, just any kind of an object. Here I call object.new. It could be a string. The key is that it's just unique. And one thing I didn't mention previously was that with queues, where we're calling queue.pop, if there's nothing in the queue, then it will actually put that thread to sleep. It'll just kind of sit there and wait. So it's really convenient for performance reasons, because you're not going to be sitting there and using up idle CPU time. But it also means if you need to communicate with your thread in some way, you have to push something onto the queue to get it to wake up. So here, we check if the object that came off of our queue is our poison object, and then we break. And in order to use this, all we have to do is push the poison object onto our queue right before we join the thread, and that's it. Simple, right? Yeah, not too bad. OK, so for me, this kind of stuff is fun. And it's not necessarily something that you get to do all day, every day. I'm going to put these slides up online, and you can walk through them. And as an exercise, maybe if you're interested in this, you can build a multiple threads with multiple workers. And if you're going to do that, if you're going to poison them, you need to poison multiple times. I know it sounds harsh to be poisoning your objects, but it's OK. They come back. All right. So threads are not evil. The GVL is not magic. There are some other thread constructs that if you're going to be using threads quite a bit, you might want to know about. For example, mutex and condition variables. Mostly if you're going to be using this pattern, you don't need to know about it. Also, this is still just for fun. This isn't necessarily a thing that you need to be writing into your Rails programs. If you're asking me and saying, OK, well, how have you actually used threads? I use threads in my libraries. For example, I use an example of a library that I use inside of my libraries is Concurrent Ruby. Well, previously we were writing a fun project, a fun library for our threading library. I don't recommend you use that in production. I recommend you use somebody else's fun library in production, which is Concurrent Ruby. So previously, where we put hello world 10 times in a different worker pool, that's exactly what this code is doing. It's a little bit simpler. We create a concurrent promise, we call execute on it, and then we pass it a block. And it will execute that in the background. The task immediately starts running in another thread. And if you're going to use this, then you have to call wait on the result at a future time. Otherwise, if there's an exception or any kind of errors in it, then it'll just happen without you ever knowing. OK, so I'm the maintainer of a library called Sprockets. Has anybody ever heard of Sprockets? OK, have you ever heard of Rails? OK. So I inherited Sprockets, and one of the things that Sprockets used to do that it stopped doing was gzipping files. So compressing a file and then writing it to disk. And I wanted to reintroduce this behavior because I thought it was really convenient to do that once at the beginning and then never have to do it again. So after we process an asset, we have to write it to disk. And I also wanted to write it as a gzip file. So file writes release the GVL, so I thought this was a good case to use threads. And I used Concurrent Ruby. Inside of Sprockets, we have a thing called a exporter, and this is just kind of an abstraction. And we loop through all of our exporters and build a series of promises. When we're done, we store each of those promises on an array. And then after we've done that for each of our exporters, we loop through them and call wait to make sure, with an exclamation point, to make sure that they're all done. And that if there's any exceptions, we hear about them. So the common pattern is we find where the GVL is released, which happens to be I/O, so the GVL is released during I/O. And when there's I/O, then threads are an amazing, amazing construct and good use for performance. We create a job, we make sure that job finishes, and then we handle any kind of shared variable access through atomic structures, which I didn't really talk about except for the queue. OK, have you all heard of a thing called guilds? OK, I see some smiles and some nods. You're probably like, I don't need to know anything about threads because guilds are going to come along. So guilds are a hypothetical way to execute multiple Ruby code in parallel. It's a kind of a feature proposal by Koichi Sasada. Judging by the video, it looks like he was speaking here, so maybe he talked about guilds. So even when guilds are, well, so first of all, guilds aren't released, so we can't quite use them yet. And even when they are, it's still going to be not as primitive of a construct as a thread. We looked at what a thread is. It's basically a process minus a couple of things. So there are still cases where a thread can be useful. OK. In 1875, there was an expedition that went to the North Pole. Within days of leaving the ship, people were succumbing to scurvy. By the end of the expedition, nearly half of the explorers had succumbed, or had scurvy. Even though it was known at the time that drinking lime juice would prevent this. The illness seemed to come at random. Some would get the symptoms, some would not. It actually turns out that what was happening is some of the explorers were killing polar bears and eating them, which fresh meat has a lot of vitamin C. Unfortunately, polar bears apparently taste disgusting. So some of the explorers were not eating that meat, and those were the ones that were getting scurvy. They didn't realize this at the time. Without a complete understanding of what caused the illness, the sailors were totally defenseless. The only working information they had was that to cure the illness, they drank lime juice. But these explorers brought lime juice with them, and they were drinking it, and so they didn't understand. Had the cure lost its effectiveness? I liken this to playing a video game where I just magically do a super move, and then for the rest of the game, I'm trying frantically to press those buttons and reproduce that super move, and it doesn't work. Without an actual working knowledge of how I made the event happen once, we can't make it happen again. People died because of this. People died because our knowledge was incomplete. And that incompleteness led to shortcuts. Because at the time, this was common knowledge. And everyone knew the cure. Also, a slow feedback cycle led to us just being wrong. One example of this in our community is Webbrick is slow. I have a blog post about this. Subscribe to my blog. This was a common idiom where at one point in time, if you were using Webbrick, it happens to use threads. And if you were using Webbrick with Ruby 1.8.7 and it's using green threads, then yes, it would be slow. If you're using Webbrick and you're using it with Rails and rack-lock, then yes, it would be slow. As it turns out, that there are good performance cases for it and good performance fits. There's also a security vulnerability in Webbrick recently, so I don't recommend using it for production. But it still goes to show that if we change our assumptions, then we have to revisit the conclusions that we make from them. Rather than remembering why Webbrick was slow, we just remembered the shorthand. We remembered Webbrick is slow as a community. And so in this day and age, it's really important to talk about what we don't know and to learn lessons and pass on that knowledge. Part of the problem from Scurvy came because doctors and scientists claimed that they knew. They claimed without fail that they truly understand the problem when they didn't. Had they been less self-assured, maybe they would have gone and conducted scientific experiments and revisited their findings. It's also important to remember that we shouldn't just remember the solutions to our problems. We have to remember the assumptions that go along with those solutions. And when those assumptions change, we have to revisit them. And this is what I ask you to do with threads. For too long, we remembered these lessons that Ruby cannot use threads. We learned that threads are not useful. We learned threads are evil. And we remembered and we repeated these things. Today, I hope I've shown you that threads are a tool, and this can be a valuable tool in your library. And when you understand them, they can be very powerful. And we can use them to make things like timers. We can use them to make things like background data collectors and use them for performance. Threads give us more than just throughput when we're blocked on I/O, not in just Ruby, but in every language. So what I'm not asking you to do today is write threaded code. You can if you want. It's a lot of fun. I really enjoy it. I'm not asking you to put threads directly in your Rails app, and I'm not asking you to be a threading expert. I share this information with you because we use threads. We use Sidekick, and we use Puma, and if you're using Sprockets. Now, Sprockets uses threads. And when we as programmers better understand the constructs that we are using, we can use them more efficiently and use them better and not be afraid of them. So I'm asking you to use Sidekick. I'm asking you to use Puma. I'm asking you to learn how to write an app that can be thread safe. Your app probably already is thread safe. Yep. Oh no, that's intentional. This is like, I'm with you. I'm with you. This is our jam session. So threads can be very useful, and threads solve real problems. No. This is intentional. Yeah. It worked a little too well. I was trying to grab your attention. So, in short, what I'm trying to tell you is that threads are not evil. Thank you very much. Spasiba.
Hello, my name is Eugene. Thanks for speech. I have several questions. First, if you correctly understand, you need a real multi-threading in your production. Did you try Rubinius, maybe Ruby on Celluloid?
So I guess the question is, have I tried Rubinius or JRuby?
In production.
Oh,
not in pet project.
In production. So I don't think Rubinius, does it even really exist anymore? I haven't heard anything from Brian in forever. I've not run anything in production in JRuby, but I have written JRuby applications. And so one of the benefits of JRuby, if you're not familiar, is that it doesn't have a GVL, and so it can actually run multiple Ruby threads at the same time, concurrently. And so you get multiple, you can utilize your CPU a lot better. With Ruby, in order to do this, you have to have multiple processes, which is why something like Puma makes sense. So you can have one process per core, and then say maybe 5 threads per process. But yeah, to answer your question, no, I haven't.
And there's additional question. I see now happen trend when guys which need performance going from Ruby to Golang, and what can you say about it if you know something?
From Ruby to another language, like Node?
To Golang, because it has threads, it has goroutines, and you can use full performance of your machine.
Yeah, I mean, so yeah, Go routines are, it's kind of like a little mini process kind of a thing with a.
It's a like item and thread pool maybe.
Yeah, and it's lightweight data sharing between those, and there's also, I think Erlang has like mini processes as well. I mean, ultimately, I love Ruby, and at Heroku, we actually write a bunch of Go. This is one of the things that it's convenient for certain applications where we really need every last millisecond. Nate Berkopec. Do you all know Nate Berkopec by any chance? Okay, there's like 2 hands. Good. So one of the things he talks about is with Ruby servers, if your request takes 100 milliseconds or your request takes 10 milliseconds, someone visiting your website can't really determine that there's a difference between that. So for me, Ruby is fast enough. And for me, it's performant enough. Also, the Ruby core team continues to do things like speed up the internals. There's a proposal for the new MJIT, which I think is going to help. I mean, ultimately, I say use the right tool for the job. And if you really need that, if you need to do concurrent processing without I/O, then Ruby is a bad fit, unless you can use multiple processes. Does that answer your question?
Yeah, thanks.
Yeah, thank you for the questions.
Hi, Richard. Thank you for the talk. And my question is about what do you think about I/O based on event loop, or how it's called, Reactor Pattern, that don't use threads, that don't use coast interleaving, but uses some core that very fast switch between futures, I think. So, what kind of I/O operation done better on this model than on the threads, and how good or bad threads in I/O waiting if you compare it with event loop and this approach.
Yes. So evented is another concurrency pattern, which it's basically what we have in JavaScript, where you only have one thread, but then as it's doing I/O, then it will allow another part of the program to run until the I/O is done, and then we fire something like a callback. There's a couple of evented libraries inside of Ruby. There's Neo for R, I think, is one of the libraries that allows you to build concurrency primitives. And there's a couple of things like Event Machine and I want to say it's called Mobius. I just went to a talk in Ruby Kaigi about this. So yes, you can use these patterns inside of Ruby. The benefit, so one of the downsides to a thread that I didn't really touch on was that when you're doing I/O inside of one thread and you need to context switch to another one, that takes time. That context switch is not free. And when you're doing evented code, you don't ever have to actually switch your thread. You're just basically switching your kind of execution context within the same code. So that's if you're doing a lot of I/O. Then you can gain some performance benefits from there. In my opinion, that Ruby, as we were talking about previously, like Ruby is not the fastest language in the world, and so in my experience, like that minute amount of time where the thread is context switching, I haven't really seen that to be like, that's never been my blocker. Normally it's because I'm like loading 1,000 active record objects or something.
Yeah, I understand.
And I will also say that I don't think that Ruby is necessarily totally built for events from the ground up. And so as a result, if you want to write an evented program in Ruby, your entire program has to be kind of event aware. If you were around when Event Machine was a thing, every single gem would be like this gem and then like this gem EM, because it had to have a special like Event Machine aware library. So I think that's kind of a downside. Personally, I've not, like, for the most part, if you make sure that your code is thread safe, which most code is nowadays, then it doesn't need to know whether it's running in a thread or not. So I just prefer that model. So good question, thank you.
Okay, I don't have very much experience with threads, but in my experience, it's harder to debug the threaded code.
Oh yes, it's much harder.
Do you have any special tricks or hints how to debug the threaded code?
So yes, turn off threads. That's the easiest way to debug threaded code. But seriously though, I normally, if I find a bug in my threaded code, I turn off the multi-threading, and then like sometimes I get really lucky and I actually see that there's a bug in my logic. When that doesn't work, my only other, in developing libraries and things, my only other trick is when you get a bug sometimes, like say maybe your tests fail 1 out of every 10 times, then I use bash to loop over my tests again and again and again and again and again until they fail. And so yes, I did mention that threads can be painful to work with. But it's kind of a price we pay. If we want the extra performance, if we want some of these features, then we have to learn to work with them. And that's and again, that's true of every language. So yeah, that's a good question. Thank you.
Thank you very much, Richard. We have a little present for you.
Thank you.
Thanks. Да, и, ребята, такие футболки можно будет купить на всякой регистрации.
Спасибо.
Пожалуйста.